Hello, my name is Matthew Janes, and this video presentation will describe resonant pile driving, a new vibratory method that uses tunable high-frequency vibrations to drive piles. The resonant method uses frequencies of 80 to 180 Hz, or 10,800 vibrations per minute. This is 5 to 10 times the frequency of conventional vibrators. Resonant vibration creates accelerations at the pile tip of 100 to 200 G and amplitudes of 4 to 8 millimeters. Accelerations of 200 G are similar to pile driving impacts. One of the many benefits of resonance is that there is no ground disturbance during pile driving. What you are witnessing is a 200 kilowatt resonant pile driver installing an AZ13 pair into dense sands that are saturated. The pile is approximately 14.6 meters long, and we're driving it through a crust of gravel about approximately 1 meter thick and then into the dense wet sands. Driving time for the 14.6 meter pile was approximately 8 minutes. As you can see, we're driving with a wine glass full of water approximately 250 millimeters from the edge of the pile, and yet there's no ripple in the wine glass. The vibration is virtually non-existent. How is this possible, and how does resonance work? Let's take a step back and look at the theory. The simplest resonance system is a pendulum that converts potential energy at the top of the swing to kinetic energy at the base of the swing. A similar pendulum system is something that we've all done and enjoyed, and that is to push a child on a swing. Welcome to sunny British Columbia, where I am going to push my son Kieran on a swing in order to demonstrate resonance. As I start to push Kieran, you can see that I need to use a lot of force with each of the initial pushes in order to get Kieran up to a given amplitude. You will see that once we have Kieran swinging at that amplitude, we don't have to add any more energy to the system, and I can in fact push him with 2 fingers, or not at all. We now have a system that's converting potential energy to kinetic energy and back again very efficiently, just like our pile when it acts as a spring. But what if I mistime my push? If I push too early, we rob the system of energy and the amplitude decays. If I push too late, we've missed the opportunity to efficiently add energy to the system, and energy is wasted. If I return to tuned pushes, look at how quickly amplitude is regained and energy is built back up in the system. Now, in order to demonstrate how we drive a pile with resonance, I am simply going to stand in Kieran's path. Pushing a child on a swing demonstrates the importance of timing the energy input to the resonant frequency of the system. Push too early, it's inefficient and the motion stops. Push too late, you're inefficient and you've missed your opportunity. Here we see the pile under the influence of a conventional vibrator. Notice that the entire pile moves up and down, and the vibrator must accelerate and decelerate the entire mass of the pile. Notice the difference under resonant vibration. Here, the pile becomes a spring, elongating under tension and shortening under compression. Returning to conventional vibration, notice the entire mass of the pile must be accelerated, decelerated, and then accelerated in the opposite direction. This requires power and high horsepower as the mass of the pile increases. Notice under resonant vibration, the center of the pile does not move. This is where the stresses are highest, as the pile moves from tension into compression. We now turn our attention to the ends of the pile, and in green you see the tips of the pile move with high accelerations and great amplitude. The pile is truly a spring, with movements at the end and compression and tension at the center of the pile. And so we see that resonance treats the pile like a spring, translating kinetic energy at the tips into stress energy at the center of the pile. The natural frequency is dominated by that of the pile and is equal to C over 2L. The dynamic energy builds up displacements and accelerations at the pile tip that allow us to drive a pile. We now turn our attention to a production pile driving site where we replaced a timber pile supported trestle with steel HP piles.
Has approximately 8 or 9 inches in between the piles. And we've trimmed the side of the hammer to slide down in between the piles. Clearance on the backside.
At this site, a total of 96 HP 360 by 132 kilogram piles were being driven to 900 kilonewton capacities. Pile lengths were 36 to 40 meters, and piles were driven with a drop hammer or Resonant Technologies RD260. Impact pile driving using an ICE 30 or a drop hammer had caused large differential settlements of the trestle as the long steel piles were being driven below the existing timber piles. The large differential settlements forced delays and extra costs on the project. Resonance Technologies' Resonant vibrator was brought in to drive the piles without ground vibration or disturbance to the neighboring structures.
We just did that pile in 3 minutes. Zero in on there and see.
It moves 4 inches at a time, if that.
Oh, I don't think it goes that far. They're saying 10, 12 blows to the foot.
That's generous.
They keep pile driving records, so we'll get one of those. And here's the one we just drove.
The project was completed with cost and schedule savings for the owner and no disruption of rail service. The CPTs show Q sub C of up to 200 bar at depth. High-strain dynamic analysis was conducted during retaps. Peak loads of 2,300 to 3,000 kilonewtons were proven. Driving times were 17 to 22 minutes. Overall, impact hammers required 60 to 80 minutes to drive the piles. Our final project involves driving of sheet piles for a Waterloo barrier adjacent to a sensitive storm sewer in Yellowknife, Yukon, northern Canada. The 6 and 8 meter sheet piles were driven easily into dense sands and gravels with the RD200 hammer. Notice that the adjacent piles are uninfluenced by the driving with the RD200. The isolation of the piles using the RD200 proved to be very useful at the end of drive, when the finished pairs did not have to be adjusted and re-pulled or driven in order to get cut off. Conventional vibratory hammers proved to cave the sides of the trench, endangering the staff, and also provided too much vibration to the sensitive storm sewer. The RD200 proved to have no influence on the storm sewer, and there was a savings when the monitoring was discontinued. We can see the lack of ground disturbance and how the adjacent finished pair is undisturbed by its neighbor being driven to final grade. Thank you for your time and interest. I look forward to answering any questions you may have.